C# and AI Masterclass by Edgar Milvis Volume 9, Chapter 11. Now, let's talk about Chapter 11, Introduction to Microsoft.ML. Turning our attention to theoretical foundations. The transition from conceptualizing AI models to deploying them on the edge, specifically within a C# ecosystem, requires a robust bridge between high-performance computational graphs and the managed, type-safe environment of .NET. This bridge is provided by Microsoft.ML, specifically through its ONNX runtime integration. To understand how we run large language models like Phi, 3 or Llama locally, we must first dissect the theoretical underpinnings of the ML.NET architecture, the mechanics of the prediction engine, and the critical process of data mapping. Turning our attention to the ML.NET architecture, a unified pipeline. At its core, Microsoft.ML is designed to bring machine learning capabilities into the .NET ecosystem, treating data processing and model inference as a composable pipeline. Unlike Python-centric frameworks that often rely on dynamic typing and loose coupling between libraries, e.g., PyTorch plus NumPy plus scikit-learn, ML.NET enforces a strict, statically typed pipeline. This architecture is crucial for edge AI because it minimizes runtime overhead and ensures memory safety, vital constraints when running on resource-limited devices. The architecture revolves around the ML context object, which acts as the factory and catalog for all operations. Think of ML context as the control tower of an airport. It doesn't handle the baggage, data, or the planes, models, itself, but it orchestrates the traffic, ensuring that every component knows where to go and how to interact. It provides a unified entry point for loading data, transforming features, and loading pre-trained models. In the context of edge AI, this architecture shifts the paradigm from training-centric to inference-centric. While ML.NET supports training, our focus for Book 9 is on the model loading and transformation phases. We are not teaching the model, we are importing a precompiled ONNX graph and feeding it data. The pipeline becomes 1. Data ingestion, defining the schema of input data. 2. Transformation, normalizing or mapping data to the tensor format expected by the ONNX model. 3. Model loading, instantiating the ONNX transformer. 4. Prediction, executing the graph. This linear flow is deterministic, which is a requirement for edge devices where unpredictable garbage collection or dynamic compilation can cause latency spikes. Now, let's talk about ONNX model integration, the universal translator. The Open Neural Network Exchange, ONNX, serves as the universal translator for AI models. In the previous chapters of this book, we discussed the fragmentation of AI frameworks, TensorFlow, PyTorch, JAX. ONNX solves this by providing a standardized format to represent machine learning models. When we integrate an ONNX model into a C# application, we are not loading a C# model, we are loading a mathematical graph of operations, nodes, and variables, tensors, that the ONNX runtime executes. The Microsoft.ML.ONNX transformer NuGet package is the specific adapter that allows ML.NET to communicate with this runtime. Analogy: the shipping container. Imagine you have a complex piece of machinery, a Llama LLM, built in a factory in Japan, PyTorch. You need to ship it to a factory in Germany, C# edge application, to be used. If you try to ship it piece by piece, it might get lost or damaged. Instead, you pack it into a standard shipping container, ONNX. This container fits onto any ship, train, or truck, Windows, Linux, Mac OS, x86, ARM. The Microsoft.ML.ONNX transformer is the crane at the German port that lifts the container off the ship and places it exactly where it needs to be on the factory floor, ready to be plugged in. In C#, this means we can take a model trained on a massive GPU cluster and run it on a Raspberry Pi or an industrial IoT gateway without changing the model's logic. The ONNX runtime handles the heavy lifting of optimizing the graph for the specific hardware, e.g., using DirectML on Windows or NumPy on Android, while ML.NET provides the C#-friendly wrapper. Turning our attention to the prediction engine, the synchronous execution core. The prediction engine T-input, T-output, is the workhorse of local inference in ML.NET. It is a wrapper around the underlying data pipeline and the loaded model, designed to make single-instance predictions. The what? It is a class that takes a generic input type, T-input, and produces a generic output type, T-output. It encapsulates the entire transformation and inference logic, presenting a simple predict, T-input-input, method. The why? In edge scenarios, we often deal with real-time streams, voice commands, sensor data, or video frames. The prediction engine is optimized for low latency, synchronous execution. It avoids the overhead of thread pooling or asynchronous state machines when the operation is inherently fast, microseconds to milliseconds. However, it is important to note that PredictionEngine is not thread-safe. It holds the state of the data pipeline. In a high-throughput edge server, you would typically pool these engines or use the transformer API directly. Analogy: the espresso machine. Think of the prediction engine as a high-end espresso machine. T input, the coffee grounds and water. T output, the espresso shot. The machine, the internal plumbing, heating elements, and pressure pumps, the ONNX runtime and data transformations. When you press the button, predict, the machine performs a synchronous sequence of operations: grinding, tamping, heating, and extracting. It happens immediately. You don't start the process and walk away, asynchronous, you wait for the result. For an edge application handling a user's voice command, this synchronous brew ensures that the response is generated before the user finishes speaking, maintaining the flow of conversation. Turning our attention to data mapping, the type-safe contract. One of the most significant challenges in bridging Python-based AI and C# is the mismatch in data types. Python relies on dynamic arrays and loose dictionaries, while C# thrives on strong typing and memory safety. Data mapping is the process of defining C# classes that mirror the tensor shapes and types expected by the ONNX model. We define public C# classes with properties that correspond to the model's inputs and outputs. For example, if a phi-3 model expects a 1D tensor of int64 long, representing token IDs, we create a class phi-3 input with a property long, input IDs. This mapping is not merely cosmetic, it is essential for the prediction engine to allocate memory correctly and marshal data between the managed.NET heap and the unmanaged native memory used by the ONNX runtime. 1. Performance. By defining the exact structure, ML.NET can pre-allocate buffers, reducing garbage collection pressure. 2. Safety. It prevents runtime errors caused by shape mismatches, e.g., trying to fit a 2D matrix into a 1D array. 3. IntelliSense and refactoring. It allows developers to use modern C# features like record types, pattern matching, and nullability checks. Analogy: the electrical adapter. Imagine you have a device, the ONNX model, that requires a specific voltage and plug shape, input tensors, float, 1, 512. You have a power source, the C# application, that provides a different format, a list float. You cannot simply jam the wires together. You need a specific adapter, the C# class, that converts the source power to the exact format the device needs. If the adapter is wrong shape or type, the device fails, runtime exception, or burns out, memory corruption. Turning our attention to visualizing the inference pipeline. To visualize how these components interact within the C# ecosystem, we can look at the data flow from the application layer down to the hardware. A diagram would show data flowing from the application layer through a C# adapter. If the adapter's shape or type is incorrect, the pipeline terminates in a runtime exception or memory corruption. Let's discuss deep dive, the role of modern C# features. In building AI applications, the choice of C# features directly impacts the efficiency and safety of the inference engine. 1. Generic constraints and reflection-free mapping. The prediction engine T-input, T-output relies heavily on C# generics. Unlike dynamic languages, C# generics are reified at runtime, meaning the type information is preserved. This allows ML.NET to inspect the properties of T-input using reflection, or source generators in newer versions, to map them to the ONNX model's input names without string matching errors. Relevance to AI. When swapping between models, e.g., Llama 2 to Llama 3, the input signature might change. By using strongly typed classes, the compiler forces you to update the input structure, catching integration errors at build time rather than during inference on the edge device. 2. Structs versus classes for tensors. While we typically use classes for T-input and T-output, for high-performance edge scenarios, like processing raw audio buffers, we might use struct types or span T. Relevance to AI. If we are running a model on an edge device with limited memory, allocating objects on the heap, classes, triggers the garbage collector, GC. A GC pause during a real-time voice interaction is catastrophic. By using stack-allocated structs or memory pools, via ArrayPool T, we can minimize GC pressure. This is a technique often used in the high-performance sections of ML.NET. 3. The iTransformer interface. Referencing the concept of interfaces from previous chapters, specifically regarding dependency injection, iTransformer is the abstraction that represents a trained model or a transformation pipeline. In the context of edge AI, this interface is vital for the model loader pattern. Relevance to AI. Just as we used interfaces to swap between OpenAI and local Llama models in Chapter 8, we use iTransformer to abstract the underlying execution engine. Whether the model is an ONNX file, a TensorFlow model, or a custom ONNX runtime session, the consuming code interacts with iTransformer. This allows for a plug-and-play architecture where the edge application doesn't care if the model is running locally or remotely, as long as the contract, the interface, is satisfied. Moving on to theoretical foundations. 1. Session options and hardware acceleration. When loading an ONNX model via ONNX transformer, we are essentially creating an inference session. The theoretical implication here is the execution provider, EP. By default, the ONNX runtime runs on CPU. However, for Edge AI, we often need GPU acceleration, DirectML on Windows, CUDA on Linux/NVIDIA Jetson. Why it matters, the PredictionEngine abstracts this, but the configuration happens at the ML context level. We must understand that the data mapping, C# to tensor, remains constant, but the underlying execution path changes. If we map a float array to a tensor, and the execution provider is set to DML, DirectML, the runtime will copy that memory to GPU via RAM. This copy operation is a hidden cost. In latency-critical apps, we must be aware of this marshalling overhead. 2. Input-output naming conventions. ONNX models are defined by a graph of nodes. The input and output nodes have specific names, e.g., input_IDs, logits. The mapping challenge, ML.NET attempts to map C# property names to ONNX node names automatically. However, if the C# property is named token IDs but the ONNX model expects input_IDs, the mapping fails. The solution, we use attributes, like column name, input_IDs, to explicitly define the contract. This is a critical theoretical concept, explicit contract definition. In edge systems, where you cannot easily debug a running process on a remote device, explicit contracts prevent silent failures. 3. Memory management and disposal. The PredictionEngine holds unmanaged resources, the ONNX session, native memory buffers. The lifecycle, unlike standard .NET objects, these are not purely managed. They implement iDisposable. The edge implication, in a long-running edge service, like a factory monitoring system, failing to dispose of PredictionEngine instances leads to memory leaks that eventually crash the system. The theoretical best practice is to treat the PredictionEngine as a scarce resource, using blocks or a singleton pattern with careful disposal logic. Now, let's talk about theoretical foundations. To run an LLM locally in C#, we are not executing C# code that mimics the model. We are, 1. Standardizing, converting the model to ONNX, the shipping container. 2. Wrapping, using Microsoft.ML ONNX transformer to wrap the native ONNX runtime, the crane. 3. Defining, creating strict C# classes, T-input, T-output, to act as the interface between managed and unmanaged memory, the adapter. 4. Orchestrating, using ML context and PredictionEngine to manage the lifecycle and execution flow, the control tower. This architecture ensures that we leverage the raw performance of native C++ libraries, ONNX runtime, while maintaining the safety, tooling, and developer experience of the .NET ecosystem. It transforms the complex, mathematical graph of a large language model into a simple, callable method, engine, predict, input. Now, let's talk about basic code example. Here is a basic code example demonstrating how to load an ONNX model and perform inference using Microsoft.ML in a C# console application. Here, we're importing all the necessary namespaces for our application. Notice Microsoft.ML and Microsoft.ML.ONNX runtime. Microsoft.ML is the core ML.NET framework, providing tools for building machine learning models and pipelines. Microsoft.ML.ONNX runtime is crucial because it's the bridge that allows ML.NET to load and execute models in the ONNX, Open Neural Network Exchange, format. This separation is by design. ML.NET can work with various model formats, and ONNX runtime provides the high-performance inference engine specifically for ONNX models. Without these, we wouldn't be able to define our data structures or interact with an ONNX model. At line 10, we declare our namespace edge_hello world. This helps organize our code and prevent naming conflicts, which is good practice in any larger C# project. Then, at line 12, we begin defining our model input class. This class is critically important because it defines the schema of the data that our ONNX model expects as input. We're telling ML.NET, hey, when you feed data into this model, expect it to look like this. If the actual input data doesn't conform to this structure, the model inference will fail. Look closely at line 20 with the column name, input, attribute. This is a vital piece of metadata. It explicitly maps the features property in our C# class to a specific input tensor name within the ONNX model. When you export a model from frameworks like PyTorch or TensorFlow to ONNX, each input and output layer gets a name. You can inspect these names using tools like netron. If this column name doesn't precisely match the input name defined in your ONNX model, ML.net won't be able to correctly identify where to feed your data, leading to runtime errors. We've chosen input here, which is a common default, but it's essential to verify this against your specific ONNX model. Similar to model input, the model output class starting at line 24 defines the schema for the data that the ONNX model will produce as output. This tells ML.net how to deserialize the model's predictions back into a strongly typed C# object. Again, the column name, output, attribute at line 29 is crucial. It maps the predictions property to the output tensor name within the ONNX model. Mismatches here will also prevent ML.net from correctly interpreting the model's results. We're expecting a float, because many machine learning models, especially regression or multi-class classification, before softmax/argmax, output vectors of floating point numbers. At line 32, we have an optional predicted label property. While our ONNX model might just output raw scores or probabilities, the predictions array, for classification tasks, it's often convenient to have a human-readable label. ML.net can automatically map the highest probability to a label if you configure it in the pipeline, or you can add post-processing logic yourself. Including this here signals that such a step might be part of a more complex classification pipeline, even if not directly used in this basic example. We begin our program class at line 36, containing the main method, the entry point of our application. At line 43, var ML context equals new ML context, seed, 0, initializes the ML context. Think of ML context as the central orchestrator for all ML.net operations. It provides access to various catalogs for data loading, transformations, training, and prediction. Setting a seed ensures reproducibility, meaning if you run the same code multiple times with the same data, you'll get the same results, which is incredibly important for debugging and scientific experimentation. Without ML context, we wouldn't be able to build or execute any ML.net pipeline. Lines 45 through 53 are dedicated to generating mock data. In a real-world application, this data would come from databases, files, or external APIs. However, for a demonstration, creating dummy data allows us to quickly test the model inference path without needing a complex data source. We're creating a list in model input, where each model input object holds a float, representing a single input sample for our ONNX model. The assumption here is that our hypothetical ONNX model expects a 1D array of 3 floats, as defined in model input sFeatures property. At line 56, we convert our dummy data list into an iData view using ML context, data.loadFromEnumerable, dummy data. The iData view is ML.net's fundamental data representation. It's an efficient, cursor-based, schematized, and immutable data structure. All ML.net components, from data transformations to model training and prediction, operate on iData view. This conversion is essential because it allows our in-memory C# objects to be processed by the ML.net pipeline, which is optimized for machine learning workflows. Here, we're setting up the model path for our ONNX model. Notice the comment at line 61, in production, use path, combine with application directories. This is a critical best practice. Hard-coding paths like model.onx assumes the model file is in the application's root directory, which might not be true in deployed environments. Path, combine ensures that your paths are correctly formed regardless of the operating system or deployment location, preventing file not found exception errors. For this simple example, we're keeping it straightforward, but always remember to use robust path handling in production. This block, from lines 65 to 77, includes a crucial check for the model file's existence. The if file exists model path condition is a safeguard. If the model.onx file isn't present, the program will print a message and exit. This is important because, unlike some ML.net scenarios where models are trained within the pipeline, here we are loading a pre-trained ONNX model. Without the actual binary ONNX file, the onx transformer cannot function. The warning at line 67 emphasizes that this dummy check is purely for making the sample code runnable. Real applications must provide a valid, pre-exported ONNX model. At line 79, we start building our ML.net data pipeline. The ML context, transforms.applyOnx model method is the core component for integrating ONNX models. We pass the model file path and, crucially, specify input column names and output column names. These arrays, new, input, and new, output, directly correspond to the column name attributes we defined in our model input and model output classes. This is how ML.net knows which columns in its iData view correspond to which tensors in the ONNX model. If these names don't match, the ONNX transformer won't be able to correctly map the data, leading to errors during model loading or inference. At line 89, bar model equals pipeline, fit, data view, might seem like we're training a model, but in the context of loading an ONNX model, fit has a different role. Since the ONNX model is already pre-trained, fit here doesn't adjust any weights or learn from data. Instead, it essentially configures the ONNX transformer within the pipeline. It performs schema validation, ensuring that the input iDataView's schema is compatible with what the ONNX model expects. It effectively finalizes the transformation chain based on the provided data schema, making the model object ready for predictions. Lines 92 to 95 are where we prepare for single-item predictions. ML context, model.create prediction engine, model input, model output, model, creates a prediction engine. This is a highly optimized, lightweight wrapper specifically designed for making predictions on one data sample at a time. It's very efficient for real-time, low-latency inference scenarios, such as web API endpoints. However, an important caveat is mentioned: it's not thread-safe. This means if you're making predictions concurrently from multiple threads, you should either create a prediction engine instance per thread or use a thread-safe pooling mechanism to avoid race conditions and incorrect results. Here, we're setting up a test input, lines 98 to 100, and then performing the actual single-item prediction using PredictionEngine, predict, test input, at line 103. This is the moment of truth where our C# object is transformed into the format expected by the ONNX model, fed through the ONNX runtime, and the output is then mapped back to our model output class. The prediction engine handles all these serialization/deserialization and inference steps seamlessly, abstracting away the complexities of interacting directly with the ONNX runtime. These lines are dedicated to outputting the results of our single-item inference to the console. It's a simple way to verify that the model ran and produced an output. String, join, comma, is a handy C# method for formatting array elements into a human-readable comma-separated string. This immediate feedback helps us confirm that our input data was correctly processed and that the model produced a result, even if we don't yet know if the result is correct in a domain-specific sense. Starting at line 110, we introduce the concept of batch prediction, which is often more performant for larger datasets than individual predictions. While PredictionEngine is great for single-item, low-latency scenarios, for processing many inputs, batching can leverage the underlying ONNX runtime's optimizations more effectively. We create a batch data list, similar to our dummy data, but now with multiple inputs. This demonstrates how you prepare multiple samples for a single inference call, which is a common pattern for throughput-oriented applications. At line 117, we convert our batch data into an iDataView named BatchView, just as we did for the single-item example. Then, at line 118, instead of using PredictionEngine, predict, we call model, transform, BatchView. This is the key difference for batch prediction. The transform method applies the entire ML.NET pipeline, which includes our ONNX model, to the entire iDataView at once, producing another iDataView containing the predictions. This approach is generally more efficient because it can minimize overhead and maximize hardware utilization, especially on GPUs. Finally, at line 122, we convert the transformed batch iDataView back into a list of model output objects, making the predictions accessible in C#. The for each loop from lines 124 to 127 iterates through the batch predictions list, printing each individual prediction. This allows us to see the output for every item in our batch. It's a clear way to confirm that the batch inference process worked as expected and that each input in the batch yielded a corresponding output. This pattern of loading data, transforming it with a model, transform, and then iterating through the results is fundamental for processing datasets with ML.NET pipelines. By scanning this code you can go to the website with more details and with buying options. On leanpub.com you can find the discounted bundle with all the volumes. This lesson is excerpted from Volume 9, Chapter 11 of the C# and AI Masterclass ebook series and from the volume Edge AI and Local Inference. Running LLMs, Llama/Phi, locally with C# and ONNX. You can find all source code here, https://github.com/edgarmilvis/C# programming series. The ebook includes 20 chapters, each one with diagrams, advanced examples, and 5 exercises with solutions. Subscribe to the channel to watch more videos. Thank you for your attention. I look forward to seeing you in the next lesson.